Okay, so I want to show you how to prove some specific theorems, right? So I want to start with some simple examples. The first one I want to prove is just this. Suppose that for all x, p of x holds, okay? Then I want to show you that that means that p of 3 must hold, right? Surely you believe that, right? If it's true for all x, then it must be true for 3. But let's actually do the proof, okay? So what's our first step, right? Step 1 is to rename quantifiers if necessary, right? In this case, we don't need to rename, okay? So we're just going to be left with the same expression. And to be clear, we're not renaming the quantifiers because there's only one. So there aren't two quantifiers with the same variable name. So that just stays the same, okay? So now let's move on to step 2. And step 2 is to migrate our quantifiers to the front, okay? So I have a for all that's kind of inside an implication. It's on the left-hand side of the implication. So I need to move it out to the front, and it will become a there exists. So this becomes there exists an x such that p of x implies p of 3. Okay, and I have to give a reason for this because I actually did something, and this is just and, or rather for all and. Okay. So that's the rule that kind of justifies that. It's just migration of quantifiers. Okay, so step 3 will be to remove the quantifiers. Okay, I have an existential, which means that I get to choose what I replace x with. Now let's see, what choice of x will make it real easy to prove that p of x implies p of 3? You got it. A really good choice of x would be x equal to 3, right? Because then this becomes p of 3 implies p of 3. I think I can prove that. So let's change this to p of 3 implies p of 3, okay? And my rationale is that I removed there exists an x with x equals to 3. Okay, so now comes the fourth step, and I didn't actually show that separately because that's what we did at the very beginning, which is just finish the proof, okay? And p of 3 implies p of 3. Well, actually, that's just equal to true, okay? And what we have here is self-implication. So there we go, QED, okay? That proof is completely done, okay? So let's try a different one. Let's now try to prove kind of, in some ways, the dual statement. P of 3 implies that there exists an x such that p of x. Okay, so let's do it again. Proof. Step 1, we want to rename quantifiers, but there's only the one quantifier, so that doesn't really do anything. Okay, so step 2, I need to migrate the quantifiers. In this case, I'm migrating a quantifier through a implication, and it's on the right side of the implication, so it actually just moves out to the front and without flipping, right? So this is just there exists an x such that p of 3 implies p of x, okay? And justification here just implies there exists, okay? All right, step 3, we want to remove the quantifiers. Again, I have a there exists, so I get to pick. What should I pick? Well, looking at what I'm going to have to prove later, p of 3 implies p of whatever I choose. What should I choose to make that proof easy? Same as before, right? Let's choose 3. So p of 3 implies p of 3, and that is remove there exists an x with x equal to 3. And step 4, which is just finish the proof, okay? This is true, once more, by self-implication. Okay, let's do another one, okay? So let's try this. For all x, p of x, if that's true, then that should imply that there exists an x such that p of x. Surely we can prove this, right? So let's see, how should we prove this? Okay, so there's actually a kind of a trap, which is what I want you to see here. So let's start And step 1, rename. Right? Actually, we do have to rename in this case because I have two x's, right? So let's say that I pick the first one to stay for all x, p of x, and that should imply that there exists a y such that p of y. Okay, so this is rename there exists x. Okay, step 2. What we need to do now is to migrate the quantifiers. Okay, all right. Now I have a choice. I can move the for all x, or I can move the there exists a y. Which one should I pick? Is it going to make a difference? I don't think it's going to make a difference. Do you think it's going to make a difference? So let's see. Let's try moving the for all x first. There exists an x such that p of x implies that there exists a y such that p of y. Okay, and as a second step, we're going to have to migrate the y. So there exists an x such that there exists a y. P of x implies p of y. Okay, and both of these are simply well, I'm renaming. So let's see, I did for all implies and implies there exists. Okay, those were the two rules. Okay, so step 3, and I need to remove the quantifiers. Okay, I have a choice when I remove the there exists an x, right? I mean, it's a there exists. So what should I choose? Actually, there's really no big reason to make the choice, right? There doesn't seem to be anything pushing me in a direction. So let me just call it c sub x, right? I don't know what I need. It doesn't seem to make a difference, right? And now I need to remove the y. Now this time, it does make a difference, right? I need to decide what is the best possible y to do. And if I'm going to prove p of c of x implies p of y, the best choice, of course, is c sub x. So I will remove the y by choosing c sub x. So in here, we removed x. And there exists an x with x equals c sub x because we had no reason to choose anything. This time we'll remove that there exists a y with y equals c sub x because that seems like the right choice to be able to finish the proof. And then step 4, finish. Actually, that's just true, right? By self-implication. Okay, so doing this example, it actually didn't matter which one I picked, right? So that's great, right? So let's do a slightly different theorem. Let's try to prove that for all x, p of x implies for all y, p of y. Okay, this should also hold, right? So the proof is probably very similar. So let's go ahead. Step 1, we need to rename quantifiers. Actually, I don't need to do anything because they're already different. Okay, so let's just write it down. Okay, now step 2, I need to migrate quantifiers. And again, I have a choice. I can migrate the x or I can migrate the y. Which one should I pick? Didn't make a difference last time, so it's not going to make a difference this time, right? So there exists an x such that p of x implies for all y, p of y. Okay, then I need to migrate the y, so there exists an x such that for all y, p of x implies p of y. All right, I'm not going to give the explanations. You've seen that many times. So now let's continue the proof. What we need to do is we need to remove the quantifiers, right? So let's remove the there exists an x. I have a choice. I can pick anything I want. What should I pick? There's no reason to pick anything over any other constant, so let's just pick c sub x. Okay, and now let's remove the for all y. But I'm removing a for all. I don't get a choice. Okay, and so it has to be a new constant c sub y. right? I can't prove this. How am I going to prove C sub y if all I know is C sub x? Something has gone terribly wrong. It actually went wrong at this step, okay? I made a bad choice. It was a bad strategy. So here's the hint for you. When you migrate quantifiers, most of the time it doesn't matter which quantifier you're going to migrate, okay? But if it does, the way that you know is because you're going to be pulling out something that is that there exists. Okay, when you pull it out, it's a there exists, right? So it might have started as a there exists, or it might be in front of a negation or something like that. But what you end up is just pulling it out as a there exists. That means that you're going to have to make a choice. We don't want to have to make choices early. We want to delay our choice until the very end, because at the very end is when we have the most information, right? At that point, I actually know what I want to choose. So for example, if I need to choose an x that is bigger than 100, I don't have a problem with that. I'll pick 150. But if I need to choose an x that is bigger than something that I haven't seen, well, I can't choose the right x. I don't know what to pick yet. Okay, so wait until all the information is known. So basically, all of this is wrong. Okay, so let's try doing the proof again, and we'll pick up right here. So let's pick it up, and step 2 is to migrate the quantifiers. But we now have a strategy, and the strategy is that we want to migrate the for alls before we migrate the there exists, right? And remember that I'm talking about for alls and there exists as they will appear in the final answer. So I could migrate the for all x, but that's going to turn into a there exists an x. Not my choice, because if I migrate the for all y, that stays as a for all y. So let's migrate that one first. For all y. For all x, p of x implies p of y. And now we have to migrate the for all x. Now there's no choice. So I have for all y, there exists an x, such that p of x implies p of y. Okay. All right. Now remember, we also talked earlier about the for all y, there exists an x was kind of weaker than the there exists an x for all y. Because for all y there exists an x lets me choose the x depending on the y. For all x there exists a y means that one x has to work for everything, right? So I do want the weaker statement, because weaker should mean easier to prove. So let's try that. Let's remove the quantifiers. Okay, for all y, I don't have a choice. That's just a new constant symbol. So there exists an x such that p of x implies p of c sub y. Now I want to remove that there exists an x. I can choose the x, and I think you can see that there's a pretty obvious choice to make. P of c sub y implies p of c sub y. Okay? And step 4, finish the proof. Shoot, this is really easy. That's just true. Okay? And it's true by self-implication. Because I waited to choose until the very end, I was able to make a good choice, and that's what made the proof go through.